right, well, let's just do a bit of a recap on some basic probability concepts that we may or may not know, and we'll just see how we go. Okay, so first things, we want to look at some Venn diagrams, which is a way of representing possible outcomes or events and how many people have selected different options, that sort of thing. First little definition here is the union, A union B. Okay, A union B means it's in A or B. So it can be one or the other, all right? The intersection A and B has to be in both. The complement, which we call A dash, okay, that means not in A, all right? So in what we call a Venn diagram where we can represent all the information, A union B, it's in A or B. So if it's inside the circle, it belongs to that set, all right? A and B, just those parts that are common to everything. And the final one there, not A, is everything not in A. So that's everything outside the circle. All right. Now, the first of our little rules guided through the use of this example here. All right. So if we do a Venn diagram representing 50 teenagers and they're asked what they did on the weekend, it can't have been this weekend because 35 of them said they went to the footy. All right. Total of 35 said they went to the football, so I'll put an F for football, or movies, or both. So we're choosing between football and the movies, okay? So I know that 35 did something. That means of the 50, 15 did nothing. So if they did nothing, they're in that little section down there where they didn't do. They were not a part of any of the activities. Let's read carefully what the rest of it says. It says, of the 22 who went to football, so there were 22 that went to football, 12 also went to the movies. So that's where the 12 of them that did both are in the intersection. So the circle for the football has to add to 22. That means I have 10 out here in the nowhere. If 22 was sort of in the football category of one shape or form, that means another 13 must have only gone to the movies because we need 35 to have done something. And once we've got the values allocated to the right sections, I can see the number of people that are in the movies and not football is 13. The number of people in not movies or not football is at 15 down here. All right. Now so if we go back to this example, if I add up all the people that went to the football, I've got 22. If I then add up all the people that went to the movies, I've got those 13, but I add that 12 in the middle twice. So the intersection gets added twice, which is why we then subtract it. Okay, to take that into ability is high 2 is what we call our addition law of probability. All right, there's not many probability laws. And what we're saying is the probability of A union B is the probability of A plus the probability of B minus the intersection. So that's my addition law of probability. All right. Now, Venn diagrams is one way we can represent probabilities. We can do the same thing in what we call a Carnot map or a probability table. And my probability table is really handy if we're looking at the probability of a lot of things not happening, A happening and B not happening, or A happening and B happening, that sort of thing. All right, so it's all intersections, and you can see how those corresponding colours marry off to the sections in the Venn diagram. What's important to note is that all the columns and rows add up. All right, the big one is if I add up the probability of A and the probability of not A happening, I get 1. If I add the probability of B plus the probability of B not happening is also 1. So my columns and rows all add up. All right. A intersection B is just the intersection point of the grid, okay, in terms of my table. So finally, if A events are such that probability of A is 0.7, A intersection B is 0.4, and A dashed intersection B is 0.2. So I've put all of those values that were given to us in the question in blue. All those green answers I can get from just adding up and filling in the gaps in the columns and rows. 0.4 plus 0.2 is 0.6. If the probability of B happening is 0.6, well, the chance of B not happening must be 0.4 or 1 minus that. I had 0.7 in there, which means the probability of A not happening must be 0.3. And we just fill in all the gaps, okay? Once we've filled in the gaps, we can just read the values out, all right? Don't forget the union. A union B is probability of A plus the probability of B minus the intersection, okay? We can do exactly the same thing for example 3. The elements in blue are the ones that I could get from the question, and then I just fill in everything else, all right? So then it's returning the probability that they don't read a book for leisure. That's just not R happening. So not R is 0.5, all right? The probability of not reading and not participating in sport, probably everyone in the COVID world, or maybe not reading, is R dash intersection S dash, and that's 0.1. Okay, just another little definition there we might add into. We talk about the terms mutually exclusive. If mutually exclusive events are events that both can't happen at the same time. It can't rain and not rain at the same time. You can't roll a dice and get an odd number and an even number, okay? So mutually exclusive events have zero intersection, and obviously if they have zero intersection, we don't have to subtract anything in common because there is no common by definition.